Hi, this is Chris Olson from the ArduPilot organization, and this is the fourth video in what has now turned into a four-video series on setup of traditional helicopters with the ArduPilot flight stack. In the first video, we looked at the various helicopter parameters in the firmware and what they are and how to set them. In the second video, we looked at servos, pitch ranges, and how to set up the mechanical part of the helicopter. In the third video, we looked at the throttle control system in ArduPilot for electric helicopters that are using governors, using mode 1 and mode 2 throttle control. In this video, we're going to look at the third mode, or mode 3, that can be used with either electric or combustion engine helicopters. And this mode uses a throttle curve, as you can see on the screen. And before we start this, let me make some explanations here on what we're looking at. First of all, I'm just going to kind of wing this one. I'm not going to use an outline, so hopefully my presentation doesn't jump around too much. The second point is that we are using firmware for this presentation that is a little bit different than the firmware in the current copter stable release. This is a development firmware that has actually completed testing, and hopefully this will be coming out in 3.6 dev. And or for our normal users, 3.6 RC1 when it comes out. The old Mode 3 system used a 3-point throttle curve that was based on 3 collective pitch positions. The maximum negative collective pitch, the 0 collective pitch point, and the H column max, or the maximum collective pitch point. And the 3 points, which would be on this graph corresponding to approximately here, here, and there at maximum pitch, had a linear interpolation between the points. It was a straight line. So this new firmware uses a 5-point curve, and it uses a spline smoothing to make the throttle curve pretty much infinitely adjustable by moving those 5 points around. And rather than looking at the firmware right away, this throttle curve is generated by a spreadsheet that uses a macro it uses a macro in the same spline math basically that creates the throttle curve in the ArduPilot firmware. I'll put it that way. So what we have here, what we're looking at in this spreadsheet, I can enter the pitch range, the negative pitch and the positive pitch. The spreadsheet calculates the collective pitch at the 5 curve points, and the 5 curve points correspond to 0, 25, 50, 75, and 100% of the collective pitch range respectively. So on the x-axis of the graph we have the collective pitch percentage, and on the y-axis of the graph we have the throttle percent that is being sent to the ESC or the governor. This curve that we're looking at right here is the traditional V throttle curve created with the new firmware with the 5 points. And for anybody that has ever set up helicopters and throttle pitch curves, this will be immediately recognizable. You know, if somebody states 95, 70, 50, 70, 100 throttle curve, just about anybody that has worked with helicopters instantly knows what you're talking about. This curve in the old firmware actually worked pretty good. It was kind of designed for the traditional V throttle curve. You can see the effects of the spline smoothing on the V part of the curve right here, where we're at 0 pitch. or approximately zero pitch at 50% collective. So that part is pretty much self-explanatory. Now, this would be a typical 3D setup with this kind of pitch range. So let's look at more UAV specific setups. Let's look at a flat throttle curve. This is a 75% flat throttle curve, and it can be used with either electric, well, technically it can be used with piston engine governors, but we're going to explain some differences there. But this is typically going to be used with an electric. In most all RC radios, when there's an electric governor in use, typically a flat throttle curve is recommended. So this would be a 75% flat throttle curve. The software just creates a straight line, so the throttle is always at 75%. So when you throw your throttle hold switch off, or in ArduPilot terms, the throttle interlock, for the purposes of this presentation, I'm going to refer to that as the throttle hold. That's the common helicopter terminology. So I'm just going to refer to that as throttle hold. So when you release your throttle hold, it goes to 75%. No matter what the collective pitch is, it's always at 75% power. The governor will use this, your electric governor. So this basically, for all practical purposes, duplicates what mode 2 does. You can set these points to 80%, 85%, 65%, whatever you want, and it will just create a flat throttle just like the mode 2 set point does. So the mode 2 is pretty much redundant from that standpoint. Let's look at a throttle curve that may be used with a typical electric helicopter. Now this curve can fly an electric helicopter without a governor. It is a 60, 62, 65, 80, 100 throttle curve. The pitch range is -2.5 to 11 degrees for a UAV setup. And electric motors typically have a lot flatter torque curve than a combustion engine does. So basically with the collective at the bottom, we're spooling up to 60% power. And this helicopter might be hovering at, say 6 to 6.5 degrees of collective pitch, somewhere in there. So we're going to be somewhere right in this portion of the graph when that helicopter is hovering. Obviously, as we go from -2.5 degrees of pitch to the 25% point where we're at about 0 degrees pitch, we don't need a lot of increase in power right in that range. And from 0 degrees pitch to 50%, which is about 4.3 degrees, we don't need a lot of extra increase in power during that portion of the collective pitch range either, because the helicopter is still going to be on the ground in a takeoff situation, and the collective pitch loading just does not increase that fast until we get to the point right in here where the helicopter starts getting light on the skids, and the amount of thrust developed by the main rotor goes up proportionately to start lifting the weight of the helicopter. Now we need to start increasing our power to our prime mover. So when we get up to, say, the 68% collective pitch range here, we're in the steep part of the curve where further increases in collective pitch increase the power quite dramatically to maintain that head speed without a governor. So that's what a typical pitch curve for an electric helicopter might look like using this 5-point throttle curve system. And of course, you would have to tweak the actual points. You can go on HeliFreak and just do a Google search. Throttle curve for throttle pitch curve for electric helicopter, and you can probably come up with 500 different recommendations on what different people are gonna recommend for a throttle curve. I mean, you get with RC heli enthusiasts, and throttle pitch curves can be talked about for hours. So this is one that I think this one's actually been flown in an electric helicopter. It worked fairly well in the particular helicopter it was flown in, and so there's an example of a throttle curve that would fly an electric helicopter without a governor. Let's look at one for a gas helicopter, which is this one. Okay, this throttle curve is a little bit different. It's a 25, 30, 35, 50, 100 curve. And piston engines typically have a pretty good throttle response up to about 50% throttle opening right at this point here. The power changes quite dramatically with gas engines from idle speed up to about 50% throttle opening, and the power output changes less dramatically from 50% throttle opening to 100% throttle opening. So we want a throttle change that is less in the range where we get up to 50% throttle opening, and then we want to increase the opening on that throttle way quicker. The particular helicopter, this is actually out of my gas helicopter. So that's the particular helicopter this curve comes from. That helicopter hovers at about 5.5 degrees of collective pitch. So we're right at the 60% collective pitch where that helicopter is hovering. So right here on this point of the curve is where the helicopter is hovering. And up to the 75% range where we increase. At that point, we are running, well, let's see here, at 60, we're running about 38% throttle or so, right at that point. And this helicopter has a governor. So the amount of change in up to the 75% collective, where we're up to 7.6 degrees of collective pitch, we're already climbing pretty good if we feed in 7.5 degrees of collective pitch. So the throttle curve starts to get steeper right there, and we're at 50% throttle. And as we feed in the rest of that collective pitch, we need that throttle to open very fast, up to 100% throttle opening at 100% collective pitch. The unique thing about this curve for a piston helicopter is that, and we'll look at this closer when we set up a gas helicopter later in this video. The unique thing about this curve is that with the collective stick all the way to the bottom, we have a 25% throttle level right there. So this helicopter can be idling, and when we release the throttle hold and it starts to spool up, leaving that collective stick at the bottom, this helicopter will spool up to what is called a ground idle rotors turning throttle setting, which engages the clutch and starts turning the main rotor and tail rotor, and it brings the rotor just above the speed where the clutch is engaged between the engine and the drivetrain on the helicopter. And this ground idle rotors turning point on the throttle curve allows a much quicker warm-up of the engine than just letting it idle at low idle without the clutch engaged. Typically 35 to 40 seconds at ground idle rotors turning will warm that engine up enough so that you can start feeding the power to it and increase the power without damaging the engine. So as we increase the collective pitch, the throttle ramps up to somewhere in this about 25% throttle range. I think I've got it set at about 25%. The governor becomes active in this helicopter. And so when the throttle reaches that point, the governor takes over and changes the speed to what the governor is set at over the next 10 seconds. So it ramps it up to rated head speed. And from that point, the governor just follows the throttle curve. And the reason this is important with piston engine governors in just about all fly-barless units and standalone governors for piston engines. They use the throttle curve for feed forward to provide a quicker throttle response. So, you know, when we're in the hover range right here, and we make a sudden collective increase up to here, the feed forward from the throttle curve is going to initially open the governor or initially open the throttle right away, rather than waiting for a sag in main rotor RPM before the governor responds. A governor can basically only respond to changes in RPM, and we don't really want that change in RPM. So just about all fly-barless unit and standalone governors use the throttle curve for feed forward to provide a quicker response on the throttle to prevent that sag in head speed that can't be corrected by the governor unless it actually senses the change in head speed. So having a proper throttle curve for a gas engine helicopter is very important. For electrics, it's really simple because this electric motors, as the load increases on an electric motor, the throttle setting stays the same. So the ESC kind of holds the same AC frequency to the motor or to the drive. And what happens in an electric motor might sag a little bit on RPMs, but it starts drawing more amps when it does that, so it automatically puts out more power. So the throttle curve for an electric is considerably flatter than it is for a piston engine because of that reason, just because of the characteristics of the two different prime movers. So the same thing happens on landing with this throttle curve. You know, you land it, you're going to be hovering right here. As you land, you bring the collective pitch down, and you drop that collective pitch all the way to the bottom, and it reduces the power and the head speed. It disengages the governor right at about this 25% point, and it allows the rotor speed to drop down to the ground idle rotors turning, and you can disengage or engage the throttle hold, and it will spool down and disengage the clutch and let the rotor spin down while the engine's idling for cool down. So that is the presentation on the different types of curves and how this software can create the curves. If we look at this curve from the standpoint of the old system, the H-Col power neg collective would be right here at 0. Zero pitch is at around 25%. So approximately right in here would be the 0 collective pitch position. So we would have 1 point here, 1 point here, and the third point would be up here. Now if you draw a line from this point to this point, you can see that throttle curve would be considerably more aggressive in the range where it doesn't have to be than this curve is. That old 3-point curve would cause way too much feed forward to the governor by the time we got right here at the hover collective point. So if we kind of draw that straight line approximately right here, we'd be over 55% throttle at hover, when the actual throttle required to hover is only about 38%. So that's the nice thing about the new 5-point curve. It can be infinitely adjusted just simply by moving those 5 points. And the spline smoothing can make curves with, let's go back to the V throttle curve. If you want, the spline smoothing can make a V throttle curve that would be fairly flat at the top end for an electric motor and fall very quickly to the V point, go back up to the 75% point, and then flatten off again for the rest of the way to 100%, just by moving the 75 and the 25 points on the curve. So the spline smoothing with the 5 points, just like the spline waypoints in mission planning for ArduPilot, make this type of a throttle curve pretty much infinitely adjustable with those 5 points by moving them around. And I don't know if I mentioned it, but this spreadsheet that we developed to visualize the throttle curve, we might make this available as a tool. It's this spreadsheet I ran in LibreOffice Calc, and it uses a macro with the same math to produce a spline curve. So Bill and I have to discuss this. We may make this available to users as a tool so they can visualize what their throttle curve looks like when they develop it. That's things we have to discuss for the future. So that pretty much explains what the new software does and what some different throttle pitch curves might look like. From there, for the second half of this video, we're going to go to an actual gas helicopter and show you how to set that up. With gas helicopters, we have a carburetor, a throttle servo. The ranges have to be set on that throttle servo. Electrics are just really simple. You just set the points with an electric, and it just works. You know, there's no ranges to set or anything like that. Most helicopter ESCs look for a value from 1,000 to 2,000 PWM, and whatever you set it to, you can pretty much tweak it, and it just kind of works. Gas engine helicopter is a little bit more complicated. So we'll cover that in the second half of the video. Okay, in this part of the video, we're going to show how to set up the throttle servo range on a gas helicopter and how to adjust the throttle curve and what the actual parameters are. So let's go to our H params and take a look. Now this is on a helicopter that has been set up. This helicopter is using the 25, 30, 35, 500, or 50, 100 throttle curve that I showed in the throttle curve graphs. But always remember that in ArduPilot, again, we have the confusing issue with these values being in PWM microseconds on a range of 0 to 1,000. So for a setting of 25% throttle, for instance, that's going to be 250 in ArduPilot, and 100% throttle is 1,000, and so on. Before you start setting up the throttle servo, go to the HRSC set point, or excuse me, the HRSC idle, right here, and make sure it's set to 0. Go to your servo params, scroll down to servo 8, which is the throttle servo. With the helicopter powered up, make sure the throttle servo with the min and max set to 1,000 and 2,000 goes in the right direction for idle. If it doesn't, you have to reverse it, just like any other servo. So at the minimum value of 1,000, that servo should move to the correct direction that corresponds to your idle position on your throttle arm, and at the maximum it should go to the wide open throttle position. Okay, so let's the first thing we're going to set is the minimum. And before you do this, let's go to the GoPro here. Hopefully I don't knock this whole assembly over. You can see that I have the throttle link off here, and there's just absolutely no way that throttle link is going to go on that ball on the carburetor. And before you do this, make sure that you back out your idle screw on the carburetor so that the throttle plate goes 100% completely closed in the throttle bore. Because that's how you're going to stop the engine with the ArduPilot system. You're not going to use the ignition switch or the ignition kill. And in fact, with a nitro engine, ignition kill won't work. So make sure that the throttle plate goes 100% completely closed, and back the throttle screw out until it does. Now we have to adjust that min value right now to get that link to go on there. So let's try, we're at 1,000. Let's try 1,200 and see what we get. We'll set the min value to 1,200 and save it. You can see it moved the servo. Well, that link is very close to going on that throttle ball, but it needs just a little bit more. So let's set it to 1250. And save it. Now that link will go on that link will go on that throttle ball absolutely perfectly. This is excellent. Now we have to set the max. So in order to do this with the ArduPilot system, and by the way, this is going to be the same way that you kind of set the range on the tail servo to get it to fit. We're just doing it here on the throttle servo, but you set your min and max the same way on the tail servo to get that link to fit. So anyway, now we have to go to the max. And to do that, make sure that your throttle curve 100 point is at the maximum of 1000. So you have 100% throttle at the maximum throttle curve point. So we're going to arm the flight controller. And we're going to throw the throttle interlock switch. We're going to release the throttle interlock. My radio has a timer in it. You heard the timer beep. That signifies the end of the run-up that is set in ArduPilot. So now we're going to advance the collective pitch all the way to the maximum, and that will advance our throttle servo to the maximum setting. We'll open the carburetor wide open and see if that link will go on there. It's just a little tiny bit long. The servo's moving just a little bit too far. So let's back that down. Let's see, we're at 2000. Let's go to 1950 and see if it fits. We'll save it. Now we are at maximum collective pitch at this point. Let's open the throttle wide open again. See if the link will go on it. And the link will go on it. That is just a little bit short of wide open throttle, but that won't matter. So right there, the link, we have the limit set on our servo. We're going to snap the link on the throttle arm. We're going to bring the throttle all the way down. We're at the bottom of the throttle curve right there. We're going to disarm. First of all, we're going to engage the throttle hold switch. Disarm the helicopter. Or disarm the flight controller. And right there, our throttle should be at the bottom. Yes, it is. The throttle's at the bottom. So there, we just set the range on the servo from 1250 to 1950 PWM. This is throttle closed. This is throttle wide open. I kind of recommend setting the servo weight trim to the same value as the min. So that's already set to 1250. I had adjusted these settings before we started here to show you how to get the range set. And so we're going to leave that at 1250. Now, let's go back to our H settings. The HRSC idle speed now has to be set. And this is the speed that is going to, or the throttle setting in PWM microseconds that is going to be required to idle your engine without the clutch being engaged. I recommend usually starting with this at 100. In this particular instance on this helicopter, it takes a value of 1200, so I'm going to set it to that. Or excuse me, 120. I'm going to save that. Okay. Like I say, I recommend starting with that at 100 or 10% throttle, and with the blades off the helicopter, take the blades off, and put your electric starter on it, and grab the head on the main rotor with one hand. Start the engine with the other, and from there you can kind of adjust that idle point to where you want it to be. But I want you to note that what happens now is that when we arm the helicopter, watch the throttle. When we armed it, the throttle moved to the idle position, and that will allow you to start the engine. And this is where you start it. Hang on to the head, start the engine. If it's idling too high and the clutch wants to disengage, make sure you have your RC radio handy, and hang on to that head. Don't let it turn and get tangled up in your starter wand if you have a top start system. And go to the RC radio and disarm it, and that will move the throttle to the closed position and stop the engine. And then if it was idling too fast, adjust that RSC idle up or down a little bit. If it wasn't idling fast enough and wanted to quit, adjust the RSC idle up a little bit. So we'll arm it. There's your idle position. The engine can be started. Now, a couple parameters here that need to be set is your ramp time and run-up time. On this helicopter, because I'm using a ground idle rotors turning throttle setting for the bottom of the throttle curve, which is 25% throttle, I'm using a fairly short ramp and run-up time. And you know, if I move the collective up to the 0 pitch range during run-up, which is going to be right here at about the HRSC throttle curve 25 point, and then disengage the throttle hold, it's going to ramp up to 30% throttle in 10 seconds instead of the 25% throttle. So this ramp and run-up time has to be set so that it ramps up in the time in the method that you like to manage your collective for spooling your helicopter up. In this particular one, like I said, I have the throttle curve, the 0 point on the throttle curve set to 25% for a ground idle rotors turning. I actually have a video clip of this. When you disengage the throttle hold, which we're going to do right now, the helicopter's armed, the engine's idling, watch the throttle servo. I just released the throttle hold. The throttle servo is very slowly ramping up. You maybe can't even see it move. But there's the timer. The run-up timer is complete. That ramped up to 25% throttle. You could probably barely see it move. And now that the run-up is complete, our throttle curve, which is set at 25, 30, 35, 50, 100, you'll see how it moves the throttle. right here, this is the bottom of the collective pitch range. This is the middle of the collective pitch range. Right there, we're at mid-stick. Now as I advance, I'm going to move the throttle starting at the bottom. We're going through middle collective right there, and now we're going at the top end of the collective range. You can see how much faster the throttle moves in the top end of that collective range versus at mid-stick. Right there, we're at mid-stick again. I'm moving the stick from about 40 to 60% back and forth. And you can see it's just making a fine adjustment to the throttle to hold head speed. But if I really lean on the collective, it opens that throttle wide open. So that's your throttle curve at work. These throttle curve points in the old software, these used to be HRSC power neg collective, HRSC power low, which was the zero pitch position, and HRSC power high, which was the high collective position. So these are the throttle curve points that we now have. They are HRSC throttle curve 0 through 100 in 25% increments, 0, 25, 50, 75, 100. So those are your 5 points on your throttle curve right there with the new parameters. Ramp run-up time we covered, the idle speed we covered. Again, do not use that idle speed for an electric. That's kind of dangerous with electric helicopters. The servo range we set. And we're ready to go. One more thing that I wanted to show is what happens when you put the collective pitch at the center stick position and do a ramp up. So let's arm the flight controller. You'll see the throttle servo snap to the idle position. We start the engine. Now we're going to move the collective pitch up to well, yeah, we'll move it up to the center stick. And we will disengage the throttle hold. Now watch the servo. In the 10 seconds there, it ramped it up to that 38% throttle hover position instead of having it at the lower end. So let's do this again. Let's disengage or engage the throttle hold. Let's disarm. Let's arm it. This time we'll leave the collective pitch at the bottom. Disengage the throttle hold and let it ramp up again. This time you'll barely see that servo move because it will only ramp it in those 10 seconds to the 25% throttle position. And there you go. So where you hold that collective pitch when you disengage your throttle hold is going to determine actually where it ramps to. And you may want to set your throttle curve accordingly. As far as setting the actual curve points themselves, I think it's going to be assumed that if you're flying piston helicopters, you're probably not a beginner, and you'll probably have a pretty good idea of where to set your throttle points depending on what engine you're using. It could be a nitro engine that may require higher throttle settings than a gasser. You know, whatever. You may be flying a turbine engine that with a FADEC controller that requires completely different settings because, you know, most turbines will have an idle speed and they don't like to run too much below about 65% torque or they have flame out problems. So if you're flying a combustion engine helicopter, we'll assume that you're probably not a beginner and have a pretty good idea of where to set your throttle curve. That's what the new software looks like and how it works. It works very, very well. And that's how you set up a gasser. So I hope you guys enjoyed watching these videos and learned a lot on how to set your helicopter up. I definitely enjoyed making them for you. And Hope all the guys and gals out there have fun with their helicopters. The ArduPilot software is, I would consider, probably the premier system for flying RC helicopters. So definitely, I hope that everybody enjoys it. Thanks for watching.